Thank you, Stefan.
I do have that.
Rang the bell. For the first speaker this afternoon is Rune Haugseng from Københavns University, who's going to talk about higher categories in higher categories.
Of higher categories.
Oh, no. Shit, I know that.
Right, so higher categories of higher categories, and so to be more precise what I mean by that, I want to talk about the following result. So we have V an En monoidal infinity category that is compatible with small colimits So this means that V has small colimits and the tensor product preserves them in each variable. Then there exists an infinity n+1 category cat, I'll call it cat infinity nv of whose objects are V enriched infinity n categories. And with the property that if I look at the infinity n category of morphisms in this infinity n+1 category from the object 1n to 1n, where 1n denotes the n category which has one object, one morphism, and so on all the way up to 1n-1 morphism. And then at the top level, the n morphisms are given by the unit in V. If you look at this infinity n category, then that is cat infinity n-1 of V. So it's kind of a de-looping of the previous category. And so the morphisms here will be some kind of iterated bimodules. If you had just functors as morphisms, then this property would just be completely false. But this implies immediately that if V is not just En monoidal, but say symmetric monoidal, or more generally En plus M, then this infinity n+1 category cat infinity nv is again symmetric monoidal, or if it was En plus M monoidal, it will be Em monoidal. Okay, so I thought I would try and actually say something about the details of how to construct this, but before I put you all to sleep with that, let me try and give some motivation for why you might want to have such a structure. So how might we hope to harness this higher structure and let me emphasize the hope here. This is this will be quite speculative, but to give you some idea. So one sort of hypothetical application would be in the context of TQFTs. Remember, an n-dimensional extended TQFT is defined to be a symmetric monoidal functor of infinity n categories. From an infinity n category board infinity n of Bordersums to some target infinity n category C. But this is sort of a very general definition with a completely abstract choice of C. And so for the kind of TQFTs that are relevant in physics and to the examples we have in low dimensions coming from representation theory, it seems like the expectation based on that is that such a kind of TQFT should assign to the point a C-linear infinity n-1 category. By C-linear, I just mean enriched in modules over C. And this expectation can be motivated both in the context of physics, having to do with boundary conditions or defects in quantum field theories, but it also fits with the examples we have in low dimensions. For example, you have the construction of Tararo-Vero, which tells you that from certain monoidal C-linear categories, which are a special kind of C-linear 2 categories, they give you 3-dimensional TQFTs. And similarly, certain kinds of braided monoidal linear categories, which are a special class of 3 categories, give you 4-dimensional TQFTs. So, so the first hope is that if we take this V here to be modules over C, like derived category of modules over C, let me just note that by cat infinity n C. And this should be the correct target for TQFTs. Like in the sense that you can actually construct these examples as extended TQFTs with this target. Okay, then the second point is in the context of higher versions of K-theory. So Boss, Dundas, Birgit Richter, and Rune Haugseng showed that well, they defined a version of algebraic K-theory, a very special kind of 2 category, and then they considered well, a category I'll call 2 category of 2 vector spaces, which is, at least morally, it's just the 2 category of certain C-linear categories. And then they showed that if you took this 2 categorical K-theory off this 2 category, you get something that's closely related to K of Ku and is of chromatic height 2. Well, I guess the chromatic height is really due to the computation of Sony and Rognes. Right. So now, based on this, we might optimistically hope that we can do something similar in higher dimensions. And So you might hope that there exists some sort of K-theory of suitable infinity n categories, and then that we can define n vect as some kind of subobject of cat infinity n c, and then the n K-theory of this n category should have something to do with the n times iterated K-theory of C, and and let's throw in the redshift conjecture and say that it should have chromatic height n. And this is maybe foreshadowed in some sense by recent work of Oyuar, Sharosky, and Sibylla, where they construct a version of K2 that's more general than what they had here, and they construct this like secondary Chern character, which looks a lot like structures that appear in chromatic homotopy theory, specifically the Hopkins-Kuhn-Ravenel character map in height 2. But this is all very speculative, obviously. And the third speculation that I want to make is in the context of higher Brauer groups. So inside of this infinity n category of cat infinity n v, we can consider the invertible objects v. So just the objects where there exists some other objects that if you tensor them together you get the unit. Well, I guess here I should assume V to be symmetric monoidal. We can consider these, and then these form, if you take the equivalences between them, they form a symmetric monoidal infinity groupoid. And moreover, it's group-like since we have inverses because we chose the invertible objects. So in the case of a ring, let's call that the nth Brauer space of the ring or ring spectrum R. So the invertible objects in cat infinity n in R modules. And then this delooping statement that I just erased tells you that if I take the loop space of the nth Brauer space of R to get the n minus first Brauer space, which means that these assemble into a non-connective spectrum. BR of R, and sort of the first parts of this are kind of familiar structure. So if you take the n equals 0, then BR 0 of R is just the units in R, and then BR1 of R is the Picard space of R, and so BR2 of R is the usual Brauer space of R. And then, well, the hope that I want to say, so we can actually understand something about these spectra in general. So we might hope that this spectrum satisfies the Tal descent. And that we can identify as homotopy groups as certain Tal cohomology groups. And maybe the most optimistic guess is that the minus nth homotopy group for this space would be something like the nth Tal cohomology group of R with coefficients in GM plus the n minus first group with coefficients in Z. And so for n equals 2, this is actually a theorem due to 2n in the case of characteristic 0, and more generally to Antio and Gepner. So
reasonable hope? Isn't it known in degree 3 already? You need to do something more sophisticated?
Well, what's known is that it probably doesn't work to take only the invertible E2 algebras.
Oh, I see. But
this is where here we're looking at the invertible infinity 2 categories, and so it's maybe that's I think still has a chance of being true.
No, I take back my answer. You're right. You take all categories.
Let me just try to get straight what is the hope and what is actually done. So the construction of these loopings comes from the theorem.
Yes, that follows from the theorem, and so the hope is that we can actually say something about them.
Does this construction for our NR or commute with if you have homotopy limit of V's, does it correspond in Bauer space? Does the construction preserve homotopy limit?
Sorry? Well, no. I mean, the problem is that you have to, this infinity n would be some kind of Siegel space, and you can see that that preserves limits in V, but then in order to get these spaces correctly defined, you have to complete it. And so that's why it's not obvious that it satisfies descent. Okay, so after that motivation, let me get back to the explaining the actual theorem, and let me start with kind of the simplest. Well, first I want to explain what I actually mean by enriched infinity n categories, and I'm going to start by just considering the simplest case of enriched infinity categories. Which, I mean, well, I guess it goes back to the paper I wrote with David Gepner. And then, well, to warm up, let's just consider the non-enriched infinity categories, and even simpler, just look at one object. Well, let me start by considering the following definition: an associative monoid in infinity category C is a simplicial object, say M going from delta up to C, such that if I look at Mn, that's equivalent to the n-fold product of copies of M1 via the maps rho I from 1 to n, which take 0 to I minus 1 and 1 to I. So this, I guess, goes back all the way to Siegel, and the idea is that M1 is the monoid, and then if we take M2, that's equivalent by this property to M1 cross M1, and that uses the outer face map. Then we still have the inner face map, which gives us a map to M1, which is the multiplication, and then if we look at M0, that's equivalent to a point by the case n equals 0 with this property, and then we have the degeneracy map to M1, and that gives the unit for the multiplication. Next, following RESC, we can upgrade this slightly to the notion of what I'll call a Siegel object or a Siegel delta object. You see, so it's another, again, a simplicial object. Say X. It satisfies a similar property where now we require, instead of xn being a product, it should be an iterated fiber product of x1 over x0. This again uses the maps rho I from above, but now we also put in the maps from 0 to n. And then, of course, if we take C to be spaces, then Siegel spaces are a good model for infinity categories. We think of x0 as being the space of objects, and then x1 as the space of morphisms. It has two face maps to x0, which give you the source and target of the morphisms. And then now, if we look at x2, that's equivalent to the fiber product of x1 with x1 over x0, which we think of as a space of composable pairs of morphisms. And then we can do, again, the interface map, which now gives us a composition map to x1, the space of morphisms. Okay, so that's a good notion of an infinity category, and now we want to upgrade this to a notion of an enriched infinity category. So what am I enriching in? I'm enriching in a monoidal infinity category. So monoidal infinity category. Well, we can define this to just be an associative monoid in infinity categories. But then, so that's a simplicial object in cat infinity, but then we can equivalently view that as a fibration. So we can, so such an associative monoid gives rise to both a co-Cartesian fibration, the upper tensor delta up, also dually to a Cartesian fibration, the lower tensor to delta. Let me, if I have such V tensor, either upper or lower, then V will denote the underlying infinity category, which is the fiber at 1. So what does this, so we're going to use this V lower tensor to define the enrichment. What does this look like? So objects in this V lower tensor are sequences V1 up to Vn, where these are objects in the underlying category V, and then a morphism from V1 Vn to W1 Wm that lies over a morphism phi from n to m in delta is given by a sequence of morphisms from Vi to a tensor product of a certain subset of the W's, and if I got the indexing right, we want a tensor over the indices that lie between phi I minus 1, so strictly greater than phi I minus 1 and less than or equal to phi I of Wj. And
Heuristic definition or actual definition?
well,
Because what is tensor of Wi?
that's the I mean, it's defined using the Cartesian morphism. So you could, yeah, it's a heuristic definition, but the actual definition is the vibration corresponding to an associative monoid. So the connection to enriched categories, so we can think of this, an object v1, vn, as a kind of basic, a little enriched category. So it has objects 0, 1, up to n, and the objects in V that are the morphisms are exactly v1, v2, up to vn. So we can kind of present enriched categories by looking at maps from these things. And so we can define a notion of a Siegel presheaf on this category V lower tensor to be presheaf, say F lower tensor up into spaces, such that, well, it satisfies, a lifted version of the usual Siegel condition. So we want to say that F of V1 up to Vn is the iterated fiber product of F of V1 over, well, F of the empty list, F of V2 and so on, via the Cartesian morphisms lying over the maps that define the Siegel condition. So the Cartesian morphisms that lie over the rho i's and the maps 0 to n. And then we want to impose one more condition to get a notion of enriched categories. So that if we restrict this presheaf to the fiber over 1, which is just equivalent to V up, well, we get a functor from that into spaces, but it actually lands, because we have the projections, the face maps from 1 to 0, we can view this as landing in spaces over F of the empty list squared. But then this slice is equivalent to the functor infinity category into spaces, and then we can rearrange this as a functor from this space, F of blank squared, into presheaves on V, and I'll say that F is representable if this functor lands in the subcategory of representable presheaves. And then the claim is that this notion of a representable Siegel presheaf on V lower tensor is a reasonable notion of an enriched infinity category.
Well, can you explain or motivate? This Siegel condition looks discrete to me, but these VI's, they don't lie in a set, they lie in a structured object. Why is this reasonable to test tuples individually?
Well, let me try and explain
what this actually means.
Well, this is an object, and then I have a canonical morphism from V1, the single element list, to this list, which is the Cartesian morphism with target V1 through Vn over row 1, and so forth.
Don't these V vary in treating them said VI in capital V, but capital V is a structured object, and you're testing just individual.
But I mean, this is a natural map, so it's functorial in the V's. Okay, so then the claim is that these, because in view of V enriched infinity categories is being modeled by these representable Siegel-free sheaves. On V lower tensor. And so let me try and motivate that. So let me write X for this F of, sorry, say I have some presentable Siegel-free sheaf F. I'll just say X is the value at the empty list. So this we should think of as the space of objects of the enriched infinity category. And then if I look at F of a single object of V, that maps to X squared. I can take the fiber as a pair X comma Y. So call that FV XY. And then this representability condition is saying that there is some object, say C of XY, an object of V, such that this fiber F of V XY is equivalent to maps in V from little v to CXY. So this is then the object that gives you the morphisms from X to Y in the enriched category. And then for example, we have a map from F of V W, a map that lives over D1 to F of V tensor W. If we look at what that does in fibers, here on the fiber over X, Y, Z, here at the fiber over X, Z, then the Siegel condition and the representability tells us that this map goes from map in V, V, C, X, Y, cross maps in V, W, C, Y, Z, to maps from V tensor W to CXZ. So now if I I have such a natural family of maps, then I can put V to be CXY, W to be CYZ, and then choose the identity maps, and then we see that we get a composition map from CXY tensor CYZ to CXZ. Okay. And then, by the Unit lemma, this functor has to be given by composition with this map. And this is also equivalent to other ways of defining enriched infinity categories, which might be more reasonable to motivate. So this is again from the paper with David Gepner. So if we look at this, the infinity category of representable Siegel-free sheaves, well, there are functor to spaces given by evaluation at this empty list. This turns out to be a Cartesian fibration, and the fibers can be identified with fiber at X equivalent to algebras in V for a certain kind of generalized non-symmetric infinity opera delta of X, which you should think of as being essentially the same thing as the operand that describes enriched categories with X as the space of objects. Right. Yeah, I'm not going to go into details of what that means, but point is that this maybe sort of weird-looking definition as representable Siegel preciefs turns out to be the same thing as looking at this maybe more natural notion of algebras for a certain family of operands. Okay, so that was enriched infinity categories, but I was supposed to talk about enriched infinity n categories. So I'll talk about how you define them using delta to the n. You could do the same kind of thing using theta n if you prefer that, but if you use delta n, we basically just iterate the previous definitions. So we can consider, let's say that a Siegel delta n object or as a special case delta n monoid in an infinity category C. Well, we can inductively define that as say x going from delta n up to C, such that if I view this instead as a functor from delta up to functors delta n minus 1 up C, then this is a Siegel object or monoid, and it takes values in Siegel delta n minus 1 objects. Or for monoids, of course, in delta n minus 1 monoids.
So Rune, sorry, I have a question. Did you have built in some completeness style condition, or didn't you have to?
No, I'm ignoring completeness for this talk.
So, but then, you still call it enriched infinity categories?
Right now I'm calling them that. Yes, there is an issue of completeness. You want to invert fully faithfulness, essentially surjective functors, and we do that, but it's sort of irrelevant to this kind of algebraic structure that I'm describing.
What about a globularity condition? Is that hidden somewhere?
No, so I'm just talking. So that'll, if I understand right, what you mean by that is sort of the constancy condition, and that'll come in a bit. So I'm first going to talk about just iterating them. Right. So if we look at C being spaces, for example, and Siegel delta n spaces, model n-fold infinity categories. So think in the case n equals 2, this model double infinity categories, and then you iterate that. So if I look at some delta n space x, and then the value at some point I breaks up as some big iterated fiber product, breaks up as limit of the kind of basic building blocks, which here are x 0 dot 0, which we should think of as the space of objects, and then, well, we have x1 0 dot 0, and sort of all the guys that have 1 1 and the rest with the entry 0. So this gives us n types of 1 morphisms. And then if you look at things which have 2 entries that are 1 and everything else 0, then you get a bunch of different types of squares, and then you keep going up to the final one, which is x1 dot 1, which is a space of kind of n cubes in the n-fold category. Right. And then, well, we can define En monoidal infinity category to be a delta n monoid in cat infinity. So, I mean, the additivity theorem tells us that this definition is equivalent to other definitions of En algebras, but this is convenient here. The additivity theorem. The additivity theorem of Lurie for En, so En tensor Em is En plus M. Right. So, where did I get you? Right. So we have this, and again we can think of these, you know, in terms of vibration. So, such an En monoidal infinity category again gives us a co-Cartesian vibration V tensor over delta n up, and a Cartesian vibration V lower tensor to delta n, and then then in the same way as here, I can lift the Siegel conditions for delta n to this V lower tensor and define a notion of Siegel presheaves on that. So we again can define a notion of representable Siegel presheaf. This V lower tensor, and then the idea is that these now model V enriched n-fold infinity categories. So if you take n equals 2, these are enriched double infinity categories, and so they have objects, they have two different kinds of vertical and horizontal one morphisms. And then for every kind of square that you can make out of those, you have an object in V that is that represents the squares in the double category. Then you can again show these are also modeled by some kind of algebras. So if we look at representable Siegel presheaves on the lower tensor, well, now we're not just evaluating a single object, we want to restrict to the subcategory of delta n. I'll call it delta n bracket 0, like this. What this means is n0 is the full subcategory on objects I1 through In, where at least one of these indices is 0. The sum IT equals 0. So we have this functor, and by Siegel presheaves, I just mean that if you restrict to, any of the, the bits where a certain index is 0, then you get a Siegel n-1 space. Right, so this is a Cartesian fibration, and the fibers we can identify with certain algebras. So delta n up x in V. And this proposition is a special case for a more general result that is proved in some work in progress with Hongyi Chu. Okay, so that was the notion of an enriched n-fold category, but now we actually want to model infinity n categories. From the unenriched case, we can view those as a special kind of n-fold categories. This definition is Clark. So say that an n-fold Siegel space is a Siegel delta n space x such that if I put the first coordinate to be 0 and look at that as a functor of delta n minus 1, and this is constant, and then x1 blank should be a Siegel, should be an n minus 1 fold Siegel space. And we can also reformulate this in terms of this subcategory delta n0. So we want to say that x restricted to, right, so this condition only depends on x restricted to delta n up 0. And if I got it right, I want to say that it's the right Kahn extension of restriction to delta n minus 1 up across 0, and this restriction is n minus 1 fold Siegel. Right, so these n-fold Siegel spaces now are modeled for infinity n categories. So if we look at an object x, then now x at I breaks up into, well, we again have x0, 0, which is the space of objects. But now, all but one of these n types of 1 morphisms will just be equivalent to the objects, so they're all trivial. So the only interesting one is x1, 0, 0, which is the space of 1 morphisms, and so on up to x1, 1, which is the space of n morphisms. So now we can define in a similar way a notion of an enriched infinity n category. So it's a representable Siegel presheaf on the lower tensor such Siegel presheaf f such that the restriction to the subcategory delta n 0 again satisfies this condition star. And then this fibration here restricts to a fibration where we have V enriched infinity n categories in this sense, but now it restricts to just n minus 1 fold Siegel spaces or infinity n minus 1 categories. Yeah, maybe I should mention that it's kind of work in progress to show that this definition using representable presheaves on delta n is equivalent to the kind of iterative definition of enriched infinity n categories, where you say that a V enriched n category is a category enriched in V enriched n minus 1 categories. Right.
I know you said you didn't want to talk about the completeness condition, but I want to ask anyway. I mean, you say that you want to define the sort of correct category by just localizing at Dwyer-Conn equivalences, but can you actually identify something like the completeness condition?
Yeah, I mean, well, in the paper with David Geffner, we proved that that localization is given by the complete enriched infinity categories, meaning that you could say the underlying Siegel space that you can extract from it is complete in the sense of Resch. Okay, I see I was quite optimistic in how much time I would have. Let me at least say something about how we might construct the infinity 2 category of the infinity categories. So the idea is to consider these slices of delta over n. So we can think of the objects here as sequences I0 up to ik, where 0 is less than or equal to I0, less than or equal to so forth up to ik, which is less than or equal to n. So, I mean, this then corresponds to the morphism k to n that takes, an index t here to it. Now we can define, just as we defined Siegel objects and monoids for delta, we can define similar structures for these slices. So I can define delta over n monoids and Siegel delta over n objects as presheaves. Delta over n up to C, such that, for monoids we want x evaluated at the sequence I0 to ik to be equivalent to the product x I0 I1 cross dot with x in minus 1 ik minus 1 ik. And for the Siegel objects, we just take the fiber product over x of I1 and so on up here over ik minus 1. And now, right, the point is that delta over 1 monoids give a good notion of bimodules. So like, if I have a delta over 1 monoid, I can look at, x, I don't really. More precisely, they give you such a delta of 1 monoid gives you a pair of associative monoids and a bimodule between them. So let me not explain that, and then instead you say that if you take, instead of monoids, you take Siegel objects, then for example delta of 1 Siegel spaces give you a notion of bimodule between categories. Then delta over 2 monoid gives you three algebras, 3 monoids, and 3 bimodules between them. So the 3 monoids say x00, x11, x22. And then bimodules x01, x12, and x02. and then a x11 bilinear map from x01 cross x12 to x02. And the idea is that we want to view the bimodules as morphisms and then compose them by taking tensor products. And it turns out that this delta over 2 monad exhibits x02 as the tensor product of these other bimodules precisely as tensor product precisely if this delta over 2 monoid X is a left-Kahn extension of subcategory lambda over 2, which is the subcategory, well, lambda over n is the subcategory, full subcategory of delta over n on the sequences where you can't go up by more than 1. So I don't know. Yeah, so if we consider these extended delta over n monoids that have been extended from lambda over n, and it turns out that that satisfies the Siegel condition. So, well, let me just say that we can, as a model for the infinity 2 category of unenriched infinity categories, we can look at Siegel presheaves on delta over n, factorially in n. And we look at those that are extended from lambda over n, which I call composite. So this is a double infinity category. Wow. And then you can again do the enriched version by, instead of doing this delta over n, you look at delta over n cross over delta with V lower tensor. You look at representable Siegel presheaves on those, and then to get the infinity n version, you just do the same thing with like products of these categories. Okay, thank you very much.
Thank you. Are there any questions? Well, there's one.
Do you know anything about dualizability in these categories?
No. Not yet.
Okay. So let's see. The next talk is now, but let's have 5 minutes to stretch our legs, and let's convene in 5 minutes. And thank Rune again.